Nothing is truly empty. This is the startling secret at the heart of modern physics. We are about to explore the quantum vacuum, a realm where so-called empty space is not a void but a seething sea of hidden activity. This activity creates real, measurable forces that shape everything from the smallest atoms to the fate of the entire cosmos. By the end of this journey, you will understand how the universe pulls tangible effects from apparent nothingness. We will see how two metal plates in a vacuum can be pushed together by the void itself, and how the energy of empty space might be tearing the universe apart. How can nothing push on something, and what does this mean for our most basic ideas of reality? This idea of a true void has a long and powerful history. For centuries, the greatest thinkers imagined the ultimate emptiness as a stage. It was a featureless backdrop, a passive container where matter could move and interact according to simple, predictable rules. In the world described by Isaac Newton, space itself was just an inert coordinate grid. If you removed every atom, every speck of dust, every trace of light and heat, you would be left with pure, absolute nothing. And from pure nothing, logically, nothing can happen. An empty stage exerts no force. A blank canvas pushes on no one. This classical vacuum was the very definition of passivity. It could not push or pull, create or destroy. It simply was. This view is deeply satisfying to our intuition. We look up at the night sky between the stars and we see blackness, a void. It feels empty, it feels still. Our common sense tells us that if we could somehow place two objects in this perfect nothingness, they would just sit there untouched unless some external force acted upon them. The void itself would be irrelevant, a silent witness. This is the prediction of that older physics. From true nothingness, no force can possibly arise. But our intuition, as we are about to see, is built for a world of much larger scales and quieter energies. The universe, it turns out, has a far more interesting definition of nothing. This quiet, logical picture of the void was shattered in the early 20th century. A new theory emerged, one that rewrote the rules for reality at its smallest scales. This was quantum mechanics, and it brought with it a principle so fundamental it changed our definition of nothing forever. It is called the Heisenberg uncertainty principle. In simple terms, it states a profound limit to what we can know. You cannot simultaneously know both the exact position and the exact momentum of a particle, like an electron. The more you pin down one, the more the other becomes a blur of possibility. But this principle goes far beyond mere measurement. It is a statement about reality itself. Perfect stillness, absolute zero energy, is forbidden. If you could know a particle was perfectly at rest, you would know both its exact position, zero, and its exact momentum, also zero. The uncertainty principle says this is impossible. There must always be a tiny, irreducible jitter, a fundamental fuzziness in the fabric of existence. This jitter applies to every field in the universe, the invisible forces that fill all of space. Even in a region we would classically call empty, with all particles removed, these fields cannot sit perfectly still. They must fluctuate, they must buzz with a minimum energy. Think of it like a calm pond. In the old view, a perfect vacuum was like that pond, frozen solid, utterly motionless. The quantum view reveals that even the most placid pond has a subtle, ceaseless shimmer at the molecular level. You cannot see it from a distance, but it is always there, an intrinsic property of the water itself. So the quantum vacuum is not an empty stage. It is a seething, bubbling sea of these temporary fluctuations. Particles and their antimatter counterparts flicker into and out of existence for unimaginably brief instants, borrowing energy from the void before vanishing again. This is not a theoretical guess. The effects of this vacuum energy are woven into the very structure of the atom, subtly shifting the light that atoms emit in ways we can measure with stunning precision. The void, it turns out, is alive with potential. It is a reservoir of hidden activity, and as we will see, this activity is not just background noise. It can reach out and push on the walls of reality itself. This ceaseless shimmer of the quantum void has a name: quantum fluctuations. Picture the fabric of space not as a still pond, but as a kind of energetic foam at the tiniest imaginable scales. Within this foam, pairs of particles and their antimatter opposites spontaneously flicker into existence. An electron and a positron, for instance, can emerge from seemingly nothing, exist for a fleeting moment, and then annihilate each other, vanishing back into the background energy of the vacuum. They are often called virtual particles, and the most common of them all is the virtual photon, the quantum carrier of the electromagnetic force. Now, the word virtual is key here. These are not particles you could ever catch in a box or detect directly with a traditional instrument. They are more like temporary disturbances in the fields that fill space, borrowing energy from the void for a time so short it defies ordinary experience. This borrowing is allowed by a specific form of the uncertainty principle, one that deals with energy and time. The principle tells us that you cannot precisely know both the energy of a system and the time over which you measure it. This creates a loophole, a tiny window of opportunity. For a very brief interval, a significant amount of energy can appear out of nowhere, so long as it disappears again quickly. The shorter the loan, the larger the amount of energy that can be borrowed. This is the quantum rule that permits the vacuum to crackle with these transient events. So we have this astonishing image. Empty space is not empty at all. It is a dynamic arena where virtual particle pairs are constantly boiling up and disappearing, a seething sea of potentiality. And while these particles are virtual, their consequences are utterly real. They are not mere mathematical ghosts, they leave fingerprints on the real world. Their fleeting existence creates a subtle pressure, a kind of background hum of activity that, as we will discover, can be coaxed into producing a force you can actually measure, a force that arises from nothing but the restless energy of the void itself. To understand this force, we must look closely at one specific field, the electromagnetic field. This is the invisible force field that fills our universe, responsible for all light, all chemistry, and the very structure of matter itself. In the classical view, if you remove all light, all radio waves, all photons, you are left with an electromagnetic vacuum, a field at perfect rest. But the quantum view paints a radically different picture. Even at the theoretical limit of cold, at absolute zero where all classical motion ceases, the electromagnetic field does not fall silent. It cannot. The uncertainty principle forbids it from ever settling into a state of perfect, definite stillness. Instead, it hums with a fundamental, irreducible vibration. Physicists call these the zero-point oscillations, and the energy they represent is the zero-point energy of the vacuum. Think of it like a guitar string. Even when it is not being played, even in a perfectly quiet room, the string is not completely motionless at the atomic level. There is a tiny, eternal tremor in its structure, a quantum whisper. The electromagnetic field is like an infinite collection of these strings, each vibrating at its lowest possible note forever. This is the true nature of the quantum vacuum for light. It is not an empty stage waiting for actors. It is a seething, foaming sea of these fundamental fluctuations. Virtual photons, the quanta of the electromagnetic field, are constantly flickering in and out of existence, born from this everlasting hum. This zero-point energy is not just a mathematical curiosity, it is measurable. Its effects show up in the precise wavelengths of light emitted by atoms, and it even influences the behavior of exotic materials at temperatures near absolute zero. The void, therefore, is not passive. It is a dynamic medium charged with a latent power that is always present, always humming, waiting to reveal its influence under the right conditions. And as we will see, one of the most dramatic ways it reveals itself is by pushing two solid objects together, a phenomenon that seems to defy logic by using nothing to create motion. This restless hum of the vacuum, this sea of virtual photons, is not merely a theoretical concept. It can be coaxed into producing a force you can measure with a laboratory experiment. The phenomenon is called the Casimir effect, named for the Dutch physicist Hendrik Casimir, who predicted it in 1948. To understand it, we need a simple but powerful image. Picture two perfectly smooth, uncharged metal plates placed extremely close together in a perfect vacuum, parallel to each other. In the classical world of Newton, with a truly empty void between them, nothing should happen. The plates would feel no force, no push or pull from the nothingness that separates them. But the quantum vacuum is not nothing. It is filled with those fluctuating electromagnetic waves, virtual photons of all possible wavelengths, constantly appearing and disappearing. Now here is the crucial twist. The metal plates act as boundaries for these fluctuations. Think of them like the fixed ends of a vibrating guitar string. A guitar string can only vibrate in certain specific patterns or modes where the ends are stationary. In the same way, the electromagnetic field between the two plates can only support virtual photons whose wavelengths fit perfectly between the plates. Only certain wavelengths are allowed. Long wavelengths, waves that are simply too big to fit in the narrow gap, are excluded. They cannot exist in that confined space. Outside the plates, however, the quantum vacuum is unrestricted. Out there, virtual photons of all wavelengths, both long and short, can flicker into existence. This creates a difference in the energy density of the vacuum. There are more possible fluctuations, more virtual activity, pressing on the outside surfaces of the plates than there are pressing on the inside surfaces. The result is an imbalance, a subtle but relentless pressure. The greater activity on the outside pushes the plates inward. They are forced together by the quiet fury of empty space itself. It is a purely quantum mechanical force with no classical explanation, no traditional fields, no exchange of real particles, just the intrinsic, seething energy of the void manifesting as a tangible, attractive pull. For decades, this was a brilliant prediction waiting for technology sensitive enough to confirm it. The Casimir effect hinges on a beautiful and subtle idea that boundaries change the rules of the quantum game. To see how, we need to think about the virtual photons not as particles in the traditional sense, but as waves of possibility rippling through the electromagnetic field. In open space with no boundaries, these waves can have any wavelength whatsoever, from unimaginably long to vanishingly short. The quantum vacuum, there is a chaotic symphony playing every possible note at once. But when you introduce two solid parallel plates, you impose a strict new rule. The electromagnetic field must obey what physicists call a boundary condition. At the surface of a good conductor like metal, the field's strength must drop to zero. You can picture it like the surface of a perfectly still pond. The water cannot have a wave peak right at the solid wall. This means that between the plates, only certain specific wavelengths of virtual photons are permitted to exist. Only those waves that perfectly fit, whose peaks and troughs align just right so that their intensity is zero at both metal surfaces, can flicker into being in that narrow gap. It is like a guitar string fixed at both ends. It can only vibrate in its fundamental note or specific harmonics, nothing in between. So the spectrum of possible fluctuations between the plates is not continuous. It is a discrete set of allowed notes. Outside the plates, however, the vacuum faces no such restriction. the symphony is unrestricted, playing that full, chaotic range of wavelengths. This creates a profound imbalance. The quantum vacuum pressure, which arises from the collective push of all these virtual particles, is not the same everywhere. There are simply more possible fluctuations, more quantum hustle and bustle, occurring in the open space outside the plates than in the regimented space between them. The outside pressure is greater. It is as if you had a box with flexible walls sitting in a stormy sea, but inside the box the water is artificially calmed. The turbulent sea outside presses harder on the walls than the calm water within, and the box is crushed. In the Casimir effect, the plates are that box, and the quantum vacuum is the storm. They are not pulled together by some mysterious attraction between the plates themselves, but pushed together by the relentless, asymmetric pressure of the seething void. The force emerges because the plates, by their mere presence, sculpt the vacuum, silencing some of its voices and amplifying others, until the silence itself becomes a crushing weight. The prediction was clear, but could this ghostly force from the void actually be measured? To answer that, we need to grasp the elegant, if mind-bending, logic behind the calculation. We are not adding up real particles, but rather the potential for activity that the vacuum allows. Remember, the energy of empty space comes from all those possible fluctuations. It is like tallying every possible note a guitar string could play. Now place two plates close together. Between them, the string is clamped at both ends, so it can only play a specific set of notes, its fundamental tone and higher harmonics. Outside the plates, the string is clamped at only one end, the plate itself, and extends to infinity. It can play a much richer, continuous spectrum of sounds, every possible note from very low to unimaginably high. The quantum vacuum energy is, in a simplified sense, the sum of the energy of all these allowed notes. When physicists performed this summation for the Casimir setup, they faced an intriguing problem. Individually, each sum for inside and outside suggested an infinite amount of energy, which is not physically sensible. But infinity minus infinity can, in the careful language of physics, yield a finite, meaningful result. The key was to compare the two situations. They calculated the difference in vacuum energy between the restricted space between the plates and the unrestricted space outside. What they found was that the sum of all those allowed fluctuations outside was indeed greater than the sum of those allowed inside. The outside had more quantum possibilities and therefore a higher energy density. In our universe, systems naturally move to lower their energy. A ball rolls down a hill to a lower gravitational energy state. Here, the system of the two plates can lower its total energy if the gap between them shrinks. Why? Because as the plates move closer together, they restrict the wavelengths allowed between them even further, silencing even more of the vacuum's fluctuations in that region. This makes the imbalance with the noisy outside vacuum even stronger, but crucially, it reduces the overall vacuum energy of the entire configuration. So the plates are pulled together. The force itself, once the infinities are carefully handled, turns out to be beautifully simple and predictable. It depends only on fundamental constants, the speed of light and Planck's constant, and critically, on the distance between the plates. The closer the plates, the stronger the pull, following a precise mathematical law. This was not a vague speculation. It was a crisp, numerical prediction for a force born from pure nothingness, waiting for experiment to prove it real. The prediction was a beautiful piece of theory, but could this whisper from the void be heard in a real laboratory? The first serious attempt to listen came in the 1950s, led by a Dutch physicist named Marcus Sparnaay. His experiment was a feat of patience and precision, conducted in an era before lasers and nanotechnology. Sparnaay used two flat metal plates, carefully polished and aligned, and brought them incredibly close together to within a few micrometers. To measure the infinitesimal force, he employed a delicate torsion balance, a device that could detect the tiny twist caused by an attraction between the plates. The challenges were immense. Eliminating every source of noise was crucial, from electrostatic charges to the faintest vibrations. Even the minuscule roughness of the metal surfaces, which at such scales looked like mountain ranges, could interfere. Sparnaay's results were tentative, plagued by large experimental uncertainties, but they pointed in the right direction. He observed an attractive force, and while he could not claim definitive proof, his work was a vital first step. It showed the effect was not just a mathematical fantasy, it was something tangible, waiting in the silence between two surfaces, if only one could learn to measure it properly. The hunt was on, but the quarry was exceedingly faint. Decades later, technology finally caught up to the theory. The breakthrough came with the invention of the atomic force microscope, an instrument so sensitive it can feel the contours of individual atoms. Here was the perfect tool to probe the Casimir force. In modern experiments, scientists use not large plates, but a tiny, gold-coated sphere and a flat plate. This geometry simplifies the math and makes alignment easier. The sphere, mounted on a flexible cantilever, is brought excruciatingly close to the plate, with gaps measured in nanometers. As the sphere approaches, the Casimir force between them pulls the cantilever ever so slightly downward. A laser beam bouncing off the cantilever detects this movement with phenomenal accuracy, translating the ghostly push of the vacuum into a clear, digital signal. The results are stunningly precise. The measured force matches the theoretical predictions with remarkable agreement, following exactly the predicted dependence on distance. The closer the surfaces, the stronger the pull, just as quantum mechanics said it should. These experiments leave no room for doubt. The force is real, it is measurable, and it originates from the quantum fluctuations of the electromagnetic vacuum. We are not just inferring the activity of empty space, we are feeling its push. The void has a voice, and we have learned to hear it. This experimental confirmation does more than validate a 70-year-old prediction. It opens a door. It proves that the quantum vacuum is not a philosophical abstraction, but a physical entity with tangible consequences. It shows that nothing, as we classically imagined it, does not exist. Every cubic centimeter of empty space, from the void between stars to the gap between the atoms in the air you breathe, is alive with this latent energy, capable of exerting force under the right conditions. The Casimir effect is a direct fingerprint of that hidden reality, a reality where boundaries shape possibilities and silence can exert a crushing weight. But if the vacuum can push two plates together, what other feats might it be capable of? Could this energy of nothingness play a role in the grandest scales of the cosmos? The force that pushes two plates together is just the beginning of the story. The quantum vacuum is not a one-trick phenomenon. It is a versatile actor whose performance changes dramatically with the stage we set for it. By altering the geometry of the objects or the medium between them, we can coax the void into producing not just attraction but repulsion and even sideways forces. This reveals a deeper truth. The Casimir effect is not a single force but a family of effects, all born from the same restless energy of empty space. To see how, let us reconsider those two metal plates. Their attraction arises because the vacuum outside them is richer, more active than the vacuum within the narrow gap. But what if we could reverse that imbalance? What if we could make the vacuum between the objects more active than the vacuum outside? This is not just a thought experiment, it leads to a repulsive Casimir force. One way to achieve this is by changing what fills the gap. Imagine our two plates again, but this time, instead of empty space between them, we fill the gap with a special fluid, one whose properties cause the speed of light within it to be slower than in the vacuum outside. In such a material, the quantum fluctuations have a different character. under the right conditions, the sum of all those virtual particle energies inside the fluid-filled gap can actually become greater than the sum in the pure vacuum outside. When this happens, the pressure imbalance flips. Now, the more active, more energetic region is between the plates. The result is a push, not a pull. The plates would repel each other, held apart by the quantum pressure of the modified void. While experimentally challenging, this repulsive version of the effect has profound implications, suggesting ways to combat the stiction that plagues microscopic machines or even to engineer levitation at the nanoscale, all powered by the subtle sculpting of nothingness. Geometry plays an even more surprising role. So far, we have considered only smooth, flat surfaces. But what if those surfaces are textured, like two combs with their teeth almost meshing? This introduces the possibility of a lateral Casimir force. Picture two flat plates, but now each plate has a series of finely corrugated grooves, like a microscopic record. If these plates are brought close together with their grooves perfectly aligned, the calculation is similar to the flat plate case. But if one plate is shifted sideways so that the ridges of one plate sit above the grooves of the other, something fascinating happens. The allowed modes of the electromagnetic field, the possible vibrations of the quantum vacuum in that narrow gap, change. The vacuum energy now depends not just on the distance between the plates, but on their lateral alignment as well. This creates a force that acts sideways, parallel to the surfaces, trying to pull the plates into a configuration that minimizes the vacuum energy, often aligning the ridges with the grooves. It is a quantum version of the feeling you get when you try to slide two pieces of corrugated cardboard past each other. They want to click into a specific alignment. This lateral force demonstrates with exquisite clarity that the vacuum is not a uniform background. It is a responsive medium. Its energy landscape is shaped in intricate detail by the boundaries we place within it. The void does not merely push inward or outward. It can guide and twist, offering a form of quantum friction or orchestrated motion derived from pure geometry. These variations, from attraction to repulsion to lateral guidance, show that the Casimir effect is a rich and tunable phenomenon. It tells us that the energy of the vacuum is not a monolithic constant, but a flexible resource that depends on context. By designing structures at the nanoscale, we are learning to choreograph the dance of virtual particles, turning the silent hum of empty space into a toolkit for the future. And if we can harness these ghostly forces between tiny objects, one must wonder, what role does this vacuum energy play on the very largest stage of all? The quantum vacuum, it seems, is a responsive medium sculpted by the objects we place within it. But what if we do not just place objects but set them in motion? This leads us to phenomena that stretch our understanding of nothingness even further, into realms where motion through the void itself has consequences. Consider a single particle like an atom moving at a constant high velocity through what we would call empty space. In our everyday intuition, if there is no air to cause drag, no medium to resist, it should glide forever without slowing. The quantum vacuum, however, is not a true void. That seething sea of virtual particles presents a subtle, complex environment. A fascinating theoretical prediction suggests that even a perfectly smooth object moving at constant velocity could experience a kind of quantum friction. This is not friction in the traditional sense of bumping into things, but a more subtle resistance arising from how the moving object interacts with the ever-present vacuum fluctuations. The object's motion disturbs the delicate balance of the quantum foam around it. In its wake, it effectively excites the vacuum, stirring up the virtual particles. This process requires energy which must come from the object's own motion, potentially causing a very slight deceleration. This idea is deeply connected to another profound concept called the Unruh Effect. In simple terms, the Unruh effect says that an observer accelerating through the vacuum will perceive a warm glow of real particles, a heat bath where an inertial observer sees only empty space. Acceleration literally heats up the vacuum from the perspective of the one being accelerated. While constant velocity is different from acceleration, the underlying principle is similar. The state of the vacuum is not absolute. It depends on one's motion through it. A swiftly moving particle essentially sees a different quantum vacuum than a stationary one, and interacting with that altered vacuum can extract a tiny cost in energy. This theoretical friction is incredibly faint, so minute that it has not yet been directly observed, buried under other, stronger forces. But its mere possibility underscores a radical point. The vacuum is not a passive backdrop for the universe's drama. It is a participant whose state is relative, and motion through it is never entirely free. If motion through the vacuum has effects, then actively stirring the vacuum should produce something even more dramatic. This brings us to one of the most astonishing predictions of quantum field theory, the dynamical Casimir effect. Recall the standard Casimir effect with two stationary plates, where the restriction of virtual photons creates a steady force. Now, imagine taking one of those mirrors and vibrating it back and forth at an incredibly high speed, a significant fraction of the speed of light. You are not just shaping the vacuum, you are vigorously shaking it. What happens? The rapidly moving mirror can do something a stationary mirror cannot. It can convert the vacuum's virtual fluctuations into real, detectable photons. Think of it like a paddle moving quickly through water. A still paddle does nothing, but a paddle vibrated rapidly creates waves. In the quantum vacuum, the virtual particle pairs that constantly flicker in and out of existence near the mirror's surface get a powerful kick from its motion. When the mirror moves, it can impart energy to these virtual pairs, specifically to the virtual photons. If the mirror's vibration is fast enough, it can provide the precise energy loan needed to promote a virtual photon from its fleeting existence into a real, permanent one. The mirror literally pumps energy from its mechanical motion into the electromagnetic field, pulling particles of light out of the empty space. It is not creating energy from nothing. The energy comes from the work done to move the mirror, but it is creating real particles from the quantum potential of the void. The light produced in this way is not random. It emerges in a specific spectrum, a quantum signature of the mirror's motion. While requiring extreme technological feats, researchers have achieved analogs of this effect using superconducting circuits that mimic a moving boundary, effectively generating photons from a quantum vacuum stimulated by rapid change. This phenomenon blurs the line between the virtual and the real. It demonstrates that the vacuum is a kind of latent substance, a reservoir of potential particles, waiting for the right kind of disturbance to make them tangible. The dynamical Casimir effect shows us that empty space can be made to glow, not with heat or borrowed light, but with photons born directly from the act of stirring the nothingness itself. If we can pull light from the void by shaking a boundary, what other profound transformations might the quantum vacuum be hiding? The ghostly push of the Casimir effect is a whisper from the void we can now measure in our labs. But the influence of the quantum vacuum is not confined to the spaces between objects. It reaches deep into the heart of matter itself, leaving its signature within every single atom. This signature is etched into the very light atoms emit, and its discovery was one of the great triumphs of 20th century physics. To find it, we must look not at metal plates, but at the simplest atom in the universe, hydrogen. In the classic model of the atom, an electron orbits the nucleus like a tiny planet around a sun, occupying specific, well-defined energy levels or shells. According to the earlier quantum theory, two particular orbits in hydrogen, known as the 2s and 2p states, should have exactly the same energy. They were predicted to be degenerate, meaning an electron jumping from a higher shell down to either of these two states should emit light of precisely the same color, the same wavelength. It was a clean, symmetrical prediction, but the universe, as we have learned, is rarely so perfectly tidy. In the late 1940s, two physicists, Willis Lamb and his student Robert Rutherford, decided to put this prediction to an exquisitely sensitive test. Using microwave techniques developed during the war, they probed the hydrogen atom with incredible precision. What they found sent a shockwave through the world of physics. The two energy levels were not identical. There was a tiny but definite split between them. The electron in the 2s state had a slightly higher energy than the electron in the 2p state. This minuscule splitting became known as the Lamb shift. It was as if two identical musical strings, when plucked, produced notes that were almost but not quite the same pitch. The difference was incredibly small, but it was undeniably there, a crack in the elegant facade of the existing theory. Something was subtly altering the electron's environment, something the equations had not accounted for. The culprit, as theorists like Hans Bethe soon realized, was the quantum vacuum. Remember that seething sea of virtual photons, the zero-point fluctuations of the electromagnetic field. An electron orbiting a nucleus is not moving through a smooth, classical emptiness. It is swimming through this turbulent quantum foam. The virtual photons constantly interact with the electron, buffeting it ever so slightly. This interaction slightly smears the electron's position. It jiggles the particle in a random dance around its ideal orbit. Think of it like a person trying to walk a perfectly straight line while being gently and randomly nudged by a crowd. Their path will waver. They will spend a little less time exactly on the line. For the electron, this quantum jitter means it spends, on average, a tiny bit further from the nucleus than the old theory predicted. This changes its energy, specifically for the s-state electron, which has a probability of being extremely close to the nucleus. This smearing effect is more pronounced. Being pushed away from the intense electric field near the proton changes its energy more than it does for the p-state electron, which already tends to orbit further out. The result is that the two levels are no longer degenerate. The s-state is shifted up. The Lamb shift is a direct measure of the electron's dance with the ghostly particles of the vacuum. It is not a force pushing plates together, but a fundamental blurring of reality at the smallest scale, a permanent tremor imprinted on the atom by the restless nothingness that surrounds it. The calculation of this effect became the proving ground for a new and more complete theory, quantum electrodynamics. When theorists included the effects of the vacuum fluctuations, their predictions matched Lamb's measurement with breathtaking accuracy. The void had written its signature in light, and we had learned to read it. This discovery did more than fix a small discrepancy. It confirmed that the quantum vacuum is not just an external curiosity. It is an intimate part of every piece of matter. The atoms that build our world are forever intertwined with the silent, shimmering activity of empty space. The Lamb shift reveals a universe where atoms are forever shaped by the silent sea around them, but this interaction goes even deeper. It reaches into the very process that makes atoms glow. When an atom is excited, its electron occupies a higher energy orbit, a precarious and temporary state. Left to the rules of classical physics, that electron might simply remain there, suspended in its elevated position forever. Yet we know from countless experiments, from the steady glow of a neon sign to the precise light of a laser, that excited atoms do not stay excited. They decay, and in decaying, they emit a photon of light. This event is called spontaneous emission, and for decades, its trigger was a profound mystery. What tells the electron it is time to fall back down? In a truly empty classical void, there would be no signal, no nudge, no reason for the transition to happen at a specific moment. The atom would be frozen in its excited state, a silent monument to unused energy. The quantum vacuum provides the missing cue. That ever-present hum of electromagnetic zero-point fluctuations is more than a background, it is a conversation partner. The excited electron is constantly buffeted by the virtual photons of the vacuum. These fleeting fluctuations provide a kind of quantum whisper, a subtle probe that interacts with the electron's own electromagnetic field. This interaction offers the electron a pathway down. It is as if the vacuum is constantly asking the electron, "Are you ready?" And at a random moment dictated by probability, the electron accepts the invitation. It drops to a lower energy level, and in doing so, it releases its excess energy not back into the vague fluctuations, but as a real, detectable photon that flies away. This means the light from a neon tube, the red glow of a helium neon laser, even the faint afterglow of a firefly, is fundamentally initiated by the active nothingness of space. The vacuum is not just a medium, it is a catalyst. Without its ceaseless quantum jostling, atoms would remain excited, light would not be spontaneously born, and our universe would be a much darker, stiller place. This reframes our view of emptiness entirely. The void is not a passive stage waiting for actors to perform. It is the director, giving the signal for the performance to begin. Every spark of light that emerges from matter is, in its first instant, a collaboration between the substance of the atom and the substance of space itself. This deeper view of the vacuum as a catalyst demands a shift in perspective. To truly grasp what nothing is, we must move beyond the picture of particles popping in and out of an empty container. That image, while useful, is a simplified story. The more complete and powerful framework is quantum field theory. Here, the fundamental ingredients of reality are not particles but fields. Imagine an infinite, invisible tapestry woven through all of space and time. There is an electron field, a quark field, a photon field for the electromagnetic force, and others for every fundamental particle and force. What we call a particle, like an electron, is not a tiny, solid ball. It is a localized excitation, a concentrated knot of energy in the underlying electron field. A photon is a ripple in the electromagnetic field. In this view, the entire universe is a symphony of interacting quantum fields. So what then is the vacuum? It is the ground state of this symphony. It is the state where every field is at its lowest possible energy. But crucially, in quantum physics, the lowest possible energy is not zero. Because of the uncertainty principle, a quantum field can never be perfectly still and perfectly defined at the same time. It must have a fundamental, irreducible jitter. This jitter is what we have been calling the quantum fluctuations. They are not particles appearing in a void. They are intrinsic vibrations of the fields themselves. The vacuum is not an empty box with occasional visitors. It is the fields themselves humming at their quietest note forever. Those virtual particle pairs are manifestations of this hum, temporary resonances where the fields interact and borrow energy. This framework elegantly explains everything we have discussed. The Casimir force arises because the metal plates impose boundary conditions on the electromagnetic field, changing which vibrational modes, which specific hums, are allowed in the gap versus outside. The Lamb shift happens because the electron is a knot in the electron field, and that knot is constantly interacting with the vibrating electromagnetic field around it, smearing its position. Spontaneous emission occurs because the excited electron field is coupled to the ever-fluctuating electromagnetic field, which provides a channel for the energy to escape as a real ripple. In quantum field theory, the vacuum is the foundational stage upon which the drama of particles unfolds, but the stage itself is alive, dynamic, and full of potential. It is the silent, vibrating ground from which all something emerges. This realization leads to an inevitable and monumental question. If every cubic centimeter of space contains this irreducible hum of quantum field energy, what is the sum total of that energy across the vast expanse of the cosmos? The answer to that question confronts us with one of the greatest mysteries in all of modern physics. This foundational hum of the quantum fields presents us with a staggering calculation. If we try to simply add up the energy of all those zero-point vibrations, of every possible mode of every quantum field in every cubic centimeter of space, we arrive at a number that is not just large but mathematically infinite. The vacuum energy density by this naive sum is an endless, impossible quantity. This is the notorious vacuum catastrophe, a direct collision between the undeniable success of quantum field theory and a result that makes no physical sense. An infinite energy density would mean space itself would possess an unimaginable gravitational pull, instantly curling the universe into a microscopic knot. Clearly, our universe is not like that. So what is wrong with the math? The answer lies not in discarding the theory, but in learning how to ask it the right questions. The process is called renormalization, and while the name sounds technical, the core idea is about focusing on what we can actually measure. The infinity arises because our calculation includes vibrations of the quantum fields at all possible wavelengths, all the way down to infinitely small scales. We are adding up contributions from virtual particles with energies approaching infinity, but our current theories, like the standard model of particle physics, may not be valid all the way down to those infinitesimally tiny distances. There could be new physics, a deeper theory that takes over at a much smaller scale, like quantum gravity. We do not yet know, so physicists use renormalization as a pragmatic, brilliantly successful tool. They acknowledge that the raw, unadjusted vacuum energy is an infinite background, a kind of quantum noise floor that is present everywhere, always. Crucially, this infinite background is the same everywhere. It permeates the inside of an atom, the gap between two Casimir plates, and the depths of interstellar space equally. Since we can never turn it off or measure it in isolation, we redefine our 0 point. Imagine you are trying to weigh a feather on a scale at the bottom of the deep ocean. The water pressure is immense, pushing down on the scale from all sides with a colossal force. But that pressure is constant. If you simply reset the scale to 0 under that constant pressure, you can then accurately measure the tiny additional weight of the feather. Renormalization does something similar for the quantum vacuum. We subtract that uniform, infinite background, setting our energy 0 to the ambient hum of the universe. What we then measure and calculate are differences from that baseline. This is precisely how we get the finite, beautiful results for the Casimir force and the Lamb shift. We are not calculating the total vacuum energy. We are calculating how the vacuum energy changes when we introduce boundaries like metal plates or an atomic nucleus. The force between the plates is the difference in vacuum energy when they are far apart versus close together. The shift in the electron's energy is the difference in how the vacuum interacts with it in one orbital versus another. These are finite, measurable differences, and renormalization allows us to extract them cleanly from the infinite sea. It is a method of focusing our inquiry, of asking not what is the absolute energy of nothing, but how does that energy change when we do something to it. Through this lens, the infinities recede, and the tangible, ghostly effects of the quantum void step into the light, precise and predictable. Yet this brilliant fix leaves a profound question hanging in the air. If we have set our 0 to the ambient hum, what is the actual, finite value of that hum? The answer to that is perhaps the greatest mismatch between theory and observation in the history of science. The infinite background hum we choose to ignore holds the key to the universe's fate. This brings our story to its grandest scale, where the quantum vacuum meets the cosmos itself. The connection was first glimpsed by Albert Einstein, though he saw it as his greatest blunder. In his equations of general relativity, which describe how matter and energy curve space-time, Einstein found a troubling implication, a universe that should be either expanding or contracting. Believing the cosmos to be static and eternal, he introduced a fudge factor, a repulsive term he called the cosmological constant. This constant represented a uniform energy density inherent to space itself, a kind of anti-gravity that could precisely balance the inward pull of matter, holding the universe in a steady state. When Edwin Hubble later discovered the universe was indeed expanding, Einstein discarded the constant, calling it unnecessary, but the idea never truly went away. Decades later, with the discovery of the quantum vacuum, physicists realized something profound. The cosmological constant was not an arbitrary fudge factor. It had a potential physical source, the zero-point energy of the vacuum. If empty space truly hums with energy, then according to Einstein's own equations, that energy should have a gravitational effect. It should curve space-time. Specifically, a uniform positive energy density spread throughout the vacuum would produce a repulsive gravitational force, exactly like Einstein's cosmological constant. It seemed like a perfect marriage. The quantum vacuum could provide the physical mechanism for the cosmological constant, explaining the energy of empty space in geometric terms. But this marriage immediately spiraled into the most severe crisis in theoretical physics. When you attempt to calculate the expected value of the cosmological constant from quantum field theory, even using conservative cutoffs and not the full infinity, you get a number. And that number is monstrously, incomprehensibly large. The theoretical prediction suggests a vacuum energy density so immense that the repulsive force would have ripped apart every atom, every nucleus in the universe within a fraction of a second after the Big Bang. Galaxies, stars, planets, even chemistry itself would have been impossible. The universe would be nothing but an accelerating void, yet we are here. Our telescopes show a cosmos that is indeed expanding, and at an accelerating rate, driven by something we call dark energy. The measured density of this dark energy, which acts just like a cosmological constant, is fantastically small, but crucially, it is not zero. When you place the theoretical prediction from quantum mechanics next to the observed value from cosmology, they do not just disagree, they are catastrophically misaligned. The number from theory is larger by a factor of 1 followed by 120 zeros. That is 10 to the power of 120. To grasp this mismatch, imagine predicting the distance from Earth to the nearest star based on the best physics we have, and then measuring it with the most precise instruments, only to find the actual distance is smaller than the width of a single atom. The error is not a slight miscalculation. It is a chasm of misunderstanding so vast it suggests we are missing something fundamental about the nature of reality. This is the cosmological constant problem, a 120 order of magnitude discrepancy. It stands as the most glaring mismatch between prediction and observation in all of science, a silent scream from our equations that we do not yet know how to interpret. It tells us that while we can master the quantum vacuum's local effects, like the Casimir force, its global gravitational personality remains a profound mystery. What cancels out almost all of that colossal vacuum energy, leaving behind only the faintest whisper we call dark energy? The answer, if we ever find it, will rewrite our understanding of everything. This staggering mismatch between prediction and reality is the cosmological constant problem, and it points to a breathtaking possibility. The force accelerating our universe, the mysterious dark energy, might be the quantum vacuum itself speaking on a cosmic scale. We have seen how the vacuum can push on metal plates and blur atomic orbits, but its most profound effect could be shaping the destiny of all existence. Dark energy is the name we give to whatever is causing the expansion of the universe to speed up, not slow down. Observations of distant supernova in the late 1990s revealed this shocking acceleration, a discovery that earned a Nobel Prize. The simplest explanation within Einstein's equations is a cosmological constant, a uniform energy density inherent to the fabric of space, and what, according to quantum field theory, fills every corner of space with a uniform energy density. The quantum vacuum. The connection is irresistibly elegant, the same seething sea of virtual particles that creates the Casimir force could, through its sheer omnipresence, be generating a gentle, repulsive pressure that stretches the cosmos itself. In this view, dark energy is not a new, exotic substance. It is the oldest thing there is, the baseline hum of reality finally revealing its gravitational personality. It would be the ultimate vacuum force, not acting between objects, but acting on the stage of spacetime itself, causing the very grid of the universe to expand faster and faster. The energy of nothingness would be the engine of cosmic destiny. Yet the problem remains not in the idea, but in the numbers. Why is the observed effect so unimaginably faint compared to the theoretical cacophony? This is not a minor puzzle, it is a fundamental crisis. It suggests our understanding of the vacuum is profoundly incomplete. Perhaps the quantum fields cancel each other out in some exquisitely fine-tuned symmetry we have not yet discovered, leaving only a ghost of residual energy. Or perhaps the vacuum energy does not gravitate in the simple way we assume, and our theories of gravity need revision at the largest scales. Some physicists speculate that the vacuum we experience is not the true ground state, but a metastable one, a valley in a much larger cosmic landscape, and the value we measure is just a local accident. Others propose entirely new frameworks like the holographic principle, where the information content of a volume of space is encoded on its boundary, fundamentally changing how we calculate vacuum energy. Each of these ideas is a frontier of modern physics, a search for the missing piece that connects the furious quantum jitter to the serene, dark expansion we observe. The mystery of dark energy forces us to confront the deepest questions. Is the vacuum energy we calculate in particle physics even the same thing that curves spacetime in cosmology? Are we misreading the ledger of nothingness? The quest to solve this riddle is more than academic. It is a journey to understand why the universe is structured to allow galaxies, stars, planets, and ultimately us to exist. That faint whisper of dark energy, if it truly is the voice of the quantum vacuum, is the quietest and most powerful force in existence, holding the secret to everything that ever was or will be. So we are left with a profound duality. The vacuum is both a mathematical framework and a physical reality with measurable force. To truly hold this idea in our minds, we need a new way to picture it, to move beyond the abstract equations. We can think of the quantum vacuum not as empty space, but as a kind of medium, a subtle substance that fills the cosmos. Not the rigid, mechanical ether of 19th century physics, which was imagined as a stationary substance that light waves rippled through like sound through air. That old ether was disproven, famously, because its properties would have affected the speed of light depending on how you moved through it, an effect that was never found. The quantum vacuum is something entirely different and far more strange. It is not a substance you move through, it is the foundational state of the fields that define space itself. A useful analogy is to picture it as a kind of frothing, effervescent sea, not a sea of water, but a sea of potentiality. At every point, virtual particles bubble up and vanish like foam on the surface of an infinitely deep ocean. This sea is not still, it churns with zero-point energy, a ceaseless quantum turbulence that is the lowest energy state possible. Another powerful image is that of a superfluid, a fluid with zero viscosity that can flow without friction. Like a superfluid, the quantum vacuum has no resistance to uniform motion, which is why objects can glide through it at constant velocity without slowing down from simple drag. Yet, also like a superfluid, it can exhibit astonishing behaviors when boundaries are introduced or when it is stirred rapidly, as we saw with the Casimir and dynamical Casimir effects. This medium has defining properties. It is permeable, meaning real particles can pass through it without being fundamentally altered, because they themselves are excitations of the underlying fields. More importantly, the speed of light is not a speed relative to this vacuum medium. It is a property of the vacuum itself. In Einstein's relativity, the speed of light is a fundamental constant, the maximum speed for causality, and it is the same for all observers regardless of their motion. This is because the vacuum, the ground state of the electromagnetic field, defines the stage on which light propagates. The speed of light is essentially the natural vibration rate of spacetime when excited by an electromagnetic ripple. This is a crucial distinction from the old ether. The ether was a reference frame, a background you could theoretically measure your motion against. The quantum vacuum provides no such preferred frame. You cannot measure your absolute velocity relative to the vacuum sea because its properties, like the speed of light it dictates, are the same in all inertial frames. The vacuum is the canvas, but it is a canvas that stretches and adjusts so that the laws of physics, including the speed of its own ripples, look identical to everyone moving at constant velocity. So the vacuum is a medium, but a democratic one. It influences everything within it, yet it refuses to be used as a yardstick for absolute rest. It is both the source of ghostly forces and the guarantor of cosmic symmetry. This leads us to a pivotal question. If the vacuum is this active, structured entity, could it be manipulated? Could we engineer its properties, not just observe them? The tantalizing hum of the quantum vacuum inevitably sparks a bold question. Could we tap this sea of energy as a limitless power source? The idea of harvesting zero-point energy has fueled imaginations and speculative fiction for decades, promising a universe where every cubic centimeter of empty space holds a reservoir of usable power. It is a captivating vision, but the reality, according to our deepest understanding of physics, presents a profound and perhaps permanent barrier. The core issue lies in the very definition of the quantum vacuum. It is not a battery waiting to be drained. It is the ground state, the lowest possible energy configuration of the quantum fields. Think of it as the very bottom of a valley. You can put a ball at the bottom of a valley, and it will stay there because there is no lower place for it to roll to. The quantum vacuum is that ball, sitting at the absolute minimum energy of the system. To extract energy from it, you would need to lower it further to find a state below the very bottom. By definition, this is impossible. The vacuum is already at rock bottom. This is a principle rooted in both quantum mechanics and thermodynamics. Any device you could build to try and extract this energy would itself be made of atoms, which are already interacting with that ground state. Your machine would be sitting in the same valley, trying to pull itself up by its own bootstraps. Now, this does not mean the vacuum is inert. As we have seen, its energy density can be changed by introducing boundaries like the Casimir plates. The force between those plates comes from a difference in vacuum energy. In a sense, you are not extracting energy from the vacuum. You are using mechanical work to move the plates together. And the changing vacuum configuration converts some of that work into another form, like kinetic energy as the plates snap together. But to get a net gain, to have the vacuum do work on your system in a cycle, you run into the same fundamental wall. You would need to return the vacuum to a higher energy state to complete the cycle, which would require putting back at least as much energy as you got out, and realistically, far more due to inevitable losses. It is like using a water wheel in a river. The wheel turns because water flows from a high place to a low place. The quantum vacuum, however, is already the low place. There is no downhill flow from it to somewhere lower, so you cannot build a sustainable wheel. Furthermore, the vacuum's energy is uniform and everywhere. To extract it locally, you would need to create a region where the vacuum energy is lower than the surrounding area, a true hole in the ground state. But any such hole would immediately be filled by fluctuations from the surrounding region, just as water instantly rushes into any depression. The vacuum is self-healing, maintaining its equilibrium. This is why phenomena like the Casimir effect or spontaneous emission are not power sources. They are one-time demonstrations of how the vacuum's configuration can be altered to produce a transient effect, always at an overall energy cost. The dream of vacuum energy as a free lunch contradicts the most fundamental laws governing energy conservation and stability. While the quantum vacuum is undeniably real and full of dynamic activity, that activity represents the baseline of reality, not a minimal resource. Its power is in shaping the forces and particles of our universe, not in lighting our cities. This realization, however, does not close the book on the vacuum's potential. It simply redirects our curiosity from extraction to something perhaps even more profound. Understanding how this foundational hum dictates the ultimate fate of all we see. The impossibility of mining the vacuum for power brings us back to a more fundamental truth, that the void is not a static stage but a participant whose very nature depends on who is looking and how they are moving. This relativity of emptiness finds one of its most startling expressions in a phenomenon predicted by physicist William Unruh. Imagine you are floating in the depths of space, in what seems like a perfect, cold, dark vacuum. You are an inertial observer moving at a constant velocity, and your most sensitive instruments detect nothing but the quiet quantum hum. Now you fire your rockets. You begin to accelerate, pushing yourself forward with constant thrust. According to the Unruh effect, your perception of the void around you would undergo a radical transformation. That same empty space you just left behind would no longer feel empty. To you, the accelerating observer, the quantum vacuum would appear as a warm bath of real particles, a gentle heat radiation filling your surroundings. The faster your acceleration, the hotter this perceived bath would become. It is a profound demonstration that the state of the vacuum, what we call nothing, is not an absolute fact of the universe. It is a relative experience intimately tied to motion. The key to understanding this lies in the nature of the quantum fields themselves. For an observer at constant velocity, the ground state of the field, its quietest hum, has a specific definition. But acceleration changes an observer's connection to the fabric of spacetime. It effectively warps their horizon of perception, much like how a constantly accelerating spaceship in relativity develops a kind of event horizon behind it, a boundary beyond which information cannot reach it. This altered relationship with spacetime changes what the observer defines as the field's ground state. The quantum fluctuations that the inertial observer dismisses as virtual, temporary events get promoted or redistributed from the accelerating observer's point of view. Some of those fleeting virtual particles cross the accelerating observer's effective horizon and become real, detectable particles. They are not created from nothing. Rather, the energy for their creation comes from the work being done to accelerate the observer. The vacuum itself has not changed. Your relationship to it has. You have, in a very real sense, heated up your own slice of the void through your motion. This effect is incredibly faint for any acceleration we can realistically achieve. To feel a warmth of even 1 degree above absolute zero, you would need to accelerate at a rate quadrillions of times stronger than Earth's gravity. While direct laboratory confirmation remains elusive, the Unruh effect is considered a solid prediction of quantum field theory in curved spacetime, a close cousin to the famous Hawking radiation from black holes. Its significance is monumental. It forges a deep and suggestive link between acceleration, inertia, and the quantum vacuum. Inertia is that resistance you feel when you try to push an object, its tendency to stay at rest or in constant motion. What if that resistance is not an intrinsic property of mass alone, but a kind of interaction with the vacuum itself? Some interpretations, like the ideas behind quantum inertia, suggest that when you push an object to accelerate it, you are not just moving its mass, you are forcing it to plow through this sea of quantum fluctuations. The Unruh radiation perceived by the accelerating object could create a kind of pressure difference, a drag from the vacuum that manifests as inertia. It is a speculative but compelling idea that the ghostly particles of an accelerated vacuum might be the unseen source of that familiar feeling of weight and resistance. The Unruh effect ultimately dissolves the last vestige of the classical void. It tells us that emptiness has no single temperature, no absolute state of being. The vacuum is a chameleon, its appearance shifting with our journey through it. An astronaut coasting sees a dark, cold nothing. An astronaut under thrust sees a glowing, warm something. Both are correct. This relativity of nothingness hints that the fabric of reality is a tapestry woven from relationships, not absolutes, and our motion is one of the threads that changes the pattern we see. This relativity of nothingness reaches its ultimate extreme at the edge of a black hole. There, gravity is not just a force, but a warping of space-time so severe that it distorts the very quantum vacuum itself, with astonishing consequences. The event horizon is that point of no return, the boundary where the pull of gravity becomes so intense that not even light can escape. In the classical picture of general relativity, nothing comes out. A black hole is the ultimate cosmic sink, absorbing everything and emitting nothing, forever growing colder and darker. But when we bring quantum field theory into this extreme gravitational landscape, the picture transforms. The intense, curving gravity near the event horizon does something remarkable to the quantum vacuum. Remember, the vacuum is not empty, it is a sea of fluctuating fields. In flat, calm spacetime, these fluctuations are symmetric. Virtual particle pairs flicker into existence and annihilate each other seamlessly. But near the event horizon, gravity violently stretches and distorts spacetime. This distortion can wrench these virtual pairs apart. Imagine a virtual particle and its antimatter partner popping into existence right at the precipice. Normally, they would meet and vanish in an instant, but if the tidal forces of gravity are strong enough, one member of the pair can fall across the event horizon into the black hole, while the other is flung outward, escaping into space. From the perspective of a distant observer, the black hole has just emitted a particle. The energy for this real particle comes from the gravitational field of the black hole itself. In effect, the black hole has used its immense gravity to squeeze a real particle out of the quantum vacuum, in a process strikingly analogous to the dynamical Casimir effect, where a moving mirror creates photons. Here, the steeply curved spacetime acts as the stirring mechanism. This is Hawking radiation, a faint glow of particles predicted by Stephen Hawking. It reframes a black hole not as an eternal prison, but as a slowly evaporating object. The particle that falls in has negative energy relative to the outside universe, which reduces the black hole's mass ever so slightly. Over unimaginable eons, a solitary black hole in empty space would slowly lose mass through this quantum process, glowing slightly warmer as it shrinks, until it might eventually vanish in a final burst of energy. Hawking radiation reveals gravity as another profound way to sculpt the vacuum and extract real forces from apparent nothingness. It shows that even the most absolute cosmic boundaries are porous to the restless quantum sea, and that the void, when stretched by the strongest forces in nature, can give birth to the particles that may one day lead to its own dissolution. Hawking radiation reveals a vacuum sculpted by gravity's extreme curve, but there is another, more direct way to wrench particles from the void. It requires not a black hole's immense mass, but an electric field of almost unimaginable strength. This is the Schwinger Effect, a prediction that demonstrates with stark clarity how empty space holds a latent content of real particles, waiting for the right key to unlock them. To understand it, we must revisit our picture of the quantum vacuum. We have seen it as a sea of virtual particle-antiparticle pairs constantly flickering in and out of existence. These pairs are ephemeral, borrowing energy from the vacuum for a fleeting moment before mutual annihilation returns the lone. They are virtual, not directly detectable. The Schwinger Effect asks a daring question. What if we could make that lone permanent? What if we could provide the energy from an external source, turning those ghostly virtual pairs into lasting, real particles? The answer lies in the power of a static electric field. Imagine a region of seemingly empty space. Now, impose upon it a uniform, constant electric field of staggering intensity. This field is not fluctuating like the quantum foam. It is a steady, classical force stretching across the void. In this intense field, something remarkable can happen to those virtual pairs, particularly electrons and positrons. The electric field exerts opposite forces on the two particles. It pushes the negatively charged electron in one direction and the positively charged positron in the opposite direction. If the field is strong enough, it can do more than just jostle them. It can rip the particle and antiparticle apart, pulling them to opposite ends of the field before they have a chance to annihilate. In doing so, the field supplies the energy needed to pay off their quantum loan, promoting them from virtual fluctuations to real, independent particles. They are no longer borrowing from the vacuum, they are being funded by the external field. The vacuum itself has not been mined for energy. Instead, the field's energy is converted directly into the mass of the new particles. It is a literal creation of matter from energy, following Einstein's famous equation, but with the quantum vacuum providing the raw template, the latent possibility of what is to be created. The required field strength is astronomical, about 1.5 times 10 to the power of 18 volts per meter. To grasp that scale, the electric field needed to spark the air in a thunderstorm is about 3 million volts per meter. The Schwinger threshold is stronger by a factor of 1,000,000 billion. It is a force that would instantly tear apart any known material, a domain belonging to the most extreme environments in the universe, perhaps near magnetars or in the earliest moments after the Big Bang. While beyond our current laboratory capabilities, the Schwinger Effect is considered a robust prediction of quantum electrodynamics. It represents a different kind of vacuum force. Not a gentle pressure from restricted fluctuations like Casimir, nor a thermal glow from acceleration like Unruh, but a direct, dramatic materialization triggered by pure field strength. It shows the vacuum is not just active, it is pregnant with potential substance, a reservoir of all possible particle pairs, frozen in possibility until an immense force crystallizes them into reality. This effect completes a profound trilogy of ways the void responds to external influence. Shape it with boundaries and it pushes, move through it with acceleration and it glows. Subject it to an overwhelming field and it literally gives birth. Each phenomenon peels back a different layer of nothingness, revealing a something that is forever intertwined with the fabric of our reality. This trilogy of effects forces us to confront a question we thought was simple. What is nothing? For millennia, philosophers have wrestled with the concept of the void, a pure absence, a non-being from which nothing can arise. It is a clean, logical idea, but quantum physics reveals it as a phantom. The closest thing to nothing in our actual universe is the quantum vacuum, and it is nothing like that philosophical ideal. The vacuum is not an absence, it is a presence. It is not inert, it is dynamic. It is not featureless, it is structured by the very laws that govern reality. The philosophical void is defined by what it is not: no matter, no energy, no properties. The quantum vacuum is defined by what it is: the lowest energy state of a set of vibrant quantum fields, buzzing with fluctuations and governed by precise mathematical rules. This is a monumental shift in understanding. We are not finding activity within a pre-existing emptiness. We are discovering that what we call empty space is itself a kind of something, a substantive entity with its own personality and behavior. Think of it like the difference between silence and the quietest possible note a guitar can play. Philosophical nothingness is the silence, a complete lack of sound. The quantum vacuum is that fundamental note, the lowest vibration the instrument is physically capable of producing. It is not silent, it is humming at its minimum volume. This hum has consequences. It can resonate, it can interact, it can exert force. So when we peer into the darkness between stars, we are not looking at a void in the old sense. We are looking at a medium, a plenum, filled with this foundational activity. The universe appears to have no room for true philosophical nothingness. Every cubic centimeter of space-time is occupied by this quantum ground state. This raises a profound and perhaps unsettling possibility. If the quantum vacuum is the closest we can get to nothing, and it is brimming with latent energy and structure, then true nothingness, the absolute void of the philosophers, may not be a physical possibility at all. It may be a logical abstraction that simply cannot exist within the framework of our cosmos. The laws of physics seem to forbid absolute stillness. They mandate a minimum level of activity as the price of existence itself. The stage is not separate from the play. The stage is the first and most fundamental actor, humming with potential before any other character steps into the light. This redefinition from void to vibrant medium changes everything. It means that forces do not merely act through empty space, they emerge from its textured fabric. It means that particles are not foreign objects placed in a container. They are excitations of the same fields that constitute the container. We are not beings moving through a void. We are intricate patterns woven from the same humming tapestry that fills the apparent emptiness around us. The quantum vacuum, therefore, is not just a scientific curiosity. It is the bedrock of reality, a rich, structured entity that blurs the line between something and nothing until the distinction itself begins to fade. This hidden push from the void is not just a laboratory curiosity. It is a tangible force that engineers must now confront in the race to build ever smaller machines. As we shrink technology down to the microscopic and nanoscopic scales, entering the realms of microelectromechanical systems and nanoelectromechanical systems, the quantum vacuum steps out of the shadows and onto the factory floor. These tiny devices, with moving parts smaller than a dust mote, are the hearts of modern sensors, switches, and actuators. They are designed to operate with exquisite precision, but when their components are brought within mere nanometers of each other, a ghostly intruder appears. The Casimir force, negligible at human scales, becomes a dominant player. What was a fascinating quantum effect in a physics lab becomes a serious engineering problem called stiction. This is the spontaneous, unwanted adhesion of moving parts. Imagine designing a microscopic switch or a tiny gear for a nanorobot, only to find that the components snap together and permanently stick, pulled into contact by the relentless whisper of empty space itself. The vacuum becomes a trap, rendering delicate machines inoperable. This is a fundamental barrier to miniaturization, a point where the bizarre rules of the quantum world directly interfere with our technological ambitions. The very nothingness we rely on to separate components becomes an adhesive, forcing engineers to redesign surfaces, change materials, or introduce clever geometries to combat this attraction. It is a stark reminder that the universe's baseline activity is not passive background. It is an active participant we must learn to negotiate with. Yet, within this challenge lies a remarkable opportunity. If the vacuum can cause unwanted stiction, perhaps we can learn to harness its pull deliberately. Researchers are exploring ways to use Casimir forces for novel actuation and sensing. Instead of fighting the attraction, we could design nanoscale components where the Casimir effect is the engine. A carefully tuned gap could act as a quantum spring, with the force providing a precise, contactless pull to actuate a mirror or close a circuit. Furthermore, because the strength of the Casimir force depends so exquisitely on distance and the materials involved, it offers a potential pathway to ultra-sensitive measurement. Imagine a sensor where the slightest change in position, the presence of a single molecule, or a variation in temperature alters the quantum vacuum pressure between two surfaces, producing a detectable shift in force. We could be on the cusp of creating devices that use the quiet hum of nothingness as their power source and their guide. The void, once an obstacle, could become the most delicate tool in the nanotechnologist's kit, turning a quantum curiosity into the cornerstone of a new generation of machines that operate by dancing with the silent energy of empty space. The colossal forces we see emerging from the vacuum today are but faint echoes of its primordial power. To find its most dramatic performance, we must journey back to the very first instance after the universe began. Our leading theory for the beginning of everything, the Big Bang, presents a puzzle. Observations of the cosmic microwave background, the ancient afterglow of creation, reveal a cosmos that is remarkably uniform and flat on the largest scales. For regions of space now billions of light-years apart to have reached the same temperature, they must have once been in contact, yet in a standard Big Bang expansion, there simply was not enough time for that contact to occur. It is as if you walked into a room and found 2 cups of coffee placed miles apart, each at exactly the same temperature, without any possible connection between them. The universe, in its infancy, appears to have been perfectly coordinated in a way that defies ordinary expansion. The solution to this cosmic riddle may lie in a special state of the quantum vacuum, in a phenomenon called inflation. Imagine the universe a fraction of a second after its birth, filled not with particles and radiation as we know them, but with a unified quantum field in a peculiar condition. This field was trapped in what physicists call a false vacuum state. Think of it like a ball resting in a small dip on the side of a steep valley. The ball is not at the true bottom, the absolute lowest energy state, but it is temporarily stable, stuck in a local energy minimum. This false vacuum state possessed an extraordinarily high energy density, a kind of latent tension infused into every point of the newborn cosmos. And according to Einstein's equations, such a uniform, high energy density does not merely sit there, it generates a powerful, repulsive gravitational force. This is the cosmological constant effect, but on a scale beyond comprehension. This repulsion did not push matter apart, it pushed space itself apart. The fabric of the universe entered a phase of exponential expansion, doubling in size repeatedly over inconceivably brief intervals. In a time span far shorter than the blink of an eye, a region smaller than a proton could have been inflated to a size larger than our observable universe today. This was not an expansion of things into space, but an explosive stretching of spacetime itself. During this inflationary epoch, the colossal force came from the vacuum energy of that primordial field. The false vacuum, that temporary high-energy state, acted as an engine, driving space to expand at a rate faster than the speed of light. This explains the uniformity we see, because every part of our observable cosmos was once a tiny, connected region before inflation blew it up. It also explains the flatness, as inflation would have stretched any initial curvature of space until it appeared flat. like blowing up a balloon to enormous size, makes a small patch on its surface seem flat. Then, in a cosmic instant, the story changed. The false vacuum was unstable, like a ball finally rolling out of its shallow dip and down into the true valley below. The quantum field decayed to its true, lower energy ground state. The enormous vacuum energy of the false state was released in a fiery burst, reheating the universe and filling it with the hot plasma of particles and radiation that would eventually become everything we see. Inflation ended, and the more gradual, decelerating expansion of the classic Big Bang took over. In this breathtaking narrative, the most powerful force in the history of existence was not an explosion of matter, but a silent, relentless push from a peculiar state of nothingness. The structure of our entire cosmos, its vast scale and smooth texture, may be the permanent imprint of a vacuum fluctuation writ large across the heavens, a single quantum shout that set the stage for all of cosmic history. Yet the inflationary story, while compelling, leaves a haunting question in its wake. What became of that immense vacuum energy that drove the cosmos to inflate? According to the theory, it should have decayed away, leaving behind the vastly quieter quantum vacuum we measure today. But this is where our narrative collides with that staggering mismatch, the cosmological constant problem. The vacuum energy we predict from particle physics is still unimaginably larger than the faint dark energy we observe accelerating the universe now. This is not a minor discrepancy. It is a gap of 120 orders of magnitude, the largest mismatch between theory and observation in all of science. It suggests our understanding of the vacuum is profoundly incomplete, that some exquisite, unknown symmetry or cancellation mechanism is at work, almost perfectly neutralizing the vacuum's gravitational weight. Or perhaps our theories of gravity and quantum fields merge in a way we have not yet grasped, a unification that would resolve the problem by showing how vacuum energy truly interacts with spacetime. This mystery sits at the very heart of modern cosmology and particle physics, a silent scream from our equations that we are missing a fundamental piece of reality's puzzle. Alongside this grand enigma, researchers pursue more tangible, though no less challenging, proofs of the vacuum's active nature. The dynamical Casimir effect, where photons are pulled from the void by a rapidly vibrating mirror, has been glimpsed in sophisticated lab setups using superconducting circuits that simulate a moving boundary. But creating the effect with a literal, mechanically oscillating mirror remains a formidable engineering dream, pushing the limits of material science and control. Similarly, the Unruh effect, where an accelerating observer perceives a warm glow from the vacuum, requires accelerations so extreme they lie far beyond any current laboratory capability. Detecting this faint thermal whisper would be a monumental achievement, directly linking acceleration to the quantum structure of spacetime. These are not just technical challenges, they are frontiers. Each successful experiment would peel back another layer of nothingness, giving us a clearer view of the medium in which we are embedded. Meanwhile, theoretical work pushes into even more speculative realms, particularly where the quantum vacuum meets the extreme gravity of black holes and the birth of the universe. Theories of quantum gravity, like string theory or loop quantum gravity, attempt to describe how spacetime itself emerges from a more fundamental quantum description. In these frameworks, the very concept of the vacuum is reimagined. It may not be a smooth continuum, but a frothing, discrete foam at the Planck scale, where the notions of space and time break down entirely. Understanding the vacuum in this regime could finally explain why its large-scale energy is so small, or reveal if dark energy is not a constant at all, but a dynamic field that has evolved over cosmic history. The quantum vacuum, therefore, is not a solved chapter in physics. It is an open book with most of its pages still blank, Its mysteries drive some of the most ambitious experiments on Earth and in space, and inspire theories that stretch the limits of human imagination. Every question we answer about the void seems to unveil two more, pulling us deeper into the realization that the foundation of everything is the most complex something we have ever tried to understand. So the void is not a solved equation, but an open frontier. From a philosophical paradox to a cornerstone of modern physics, our journey reveals a universe where nothingness is the most active ingredient of all. We began with a simple classical idea, a silent stage where matter performs, but quantum mechanics shattered that stillness, introducing us to the Heisenberg uncertainty principle, a law that forbids perfect calm and mandates a ceaseless shimmer at reality's foundation. This shimmer is the quantum vacuum, not an empty container, but a seething sea of virtual particles and zero-point energy, a dynamic medium that defines the lowest possible state of existence. We saw this hidden activity reach out and touch our world in tangible ways. Two metal plates in a perfect vacuum are pushed together by the silent pressure of the void itself, a phenomenon predicted by Casimir and now measured with stunning precision in labs around the world. We discovered that this vacuum shapes the atoms themselves, causing the Lamb shift, a tiny but definitive fingerprint of quantum fluctuations in the light hydrogen emits. It even initiates the very glow of matter, acting as the catalyst for spontaneous emission, pulling real photons from the potential of empty space. The implications stretch from the infinitesimal to the cosmic. On the smallest scales, the Casimir force is a formidable challenge for nanotechnology, causing unwanted stiction, yet it also promises new forms of actuation and sensing. On the grandest scale, the energy of this quantum vacuum may be the engine behind dark energy, the mysterious force accelerating the expansion of the entire cosmos, while also potentially serving as the inflationary fuel that blew the universe into its vast, smooth state in the first fleeting moments after the Big Bang. We have encountered forces born from motion through this medium, like the Unruh Effect, and forces that tear real particles from the void, like the Schwinger Effect. We have seen how black holes can slowly evaporate by radiating Hawking radiation, a direct consequence of how extreme gravity sculpts the quantum vacuum at the event horizon. Each of these phenomena, from the gentle push on nanoscale gears to the fate of the cosmos, stems from the same profound truth: empty space is not empty. It is a substantive, structured entity, the quantum ground state from which all particles and forces emerge as excitations. This reshapes our understanding of reality at the most fundamental level. We are not separate beings moving through a void. We are intricate patterns woven from the same humming tapestry that constitutes the apparent emptiness around us. The distinction between something and nothing, once so clear, now blurs into a continuum of activity. The stage and the actors are made of the same substance. This realization is not an end, but a beginning. It opens more questions than it answers. Why is the vacuum energy we calculate so catastrophically larger than what we observe? How does the quantum description of nothingness merge with the geometry of gravity? Can we one day directly detect the Unruh glow or harness these vacuum forces in transformative technologies? The exploration of the quantum void reminds us that the universe is far stranger, more interconnected, and more generous with its mysteries than our everyday intuition suggests. To look into the dark spaces between the stars is no longer to gaze into a void, but to contemplate a vibrant, energetic plenum, the silent foundation of all that is. And if the quietest thing we know holds such astonishing power and complexity, what other wonders await in the deeper mysteries of physics, just beyond the edge of our current understanding?